In this paper, we investigate dual-arm task planning problem in the scenario of tabletop rearrangements. Object rearrangement is a basic task in our daily lives. It will be beneficial but challenging to use robot arms to clean up our kitchens, kids' rooms, food pantries, or office desktops. In rearrangement problems, the robot arm moves objects from start positions to specific goal positions. No matter in home automation or industrial automation, deploying multiple arms is a straightforward way to expand the workspace size and increase the overall system throughput. In this paper, we studied a cooperative dual-arm rearrangement problem. In this problem, two arms workspace partially overlap, and each robot is responsible for a portion of the workspace. When the placing position is out of reach, the arm hands off the object to the other arm. When the path conflict occurs, one arm yields to the other. We evaluate the solution quality by the mixspan under two levels of fidelity. In the MC mixspan, the cost of the solution is counted as action steps. This matrix mimics the scenario where the traveling time is trivial comparing with the execution time of pick and places. In the MC mixspan, the cost is the estimated execution time given the spent time of a single pick, a single place, a handoff, and the traveling speed of the end effector. In this case, the robot's pick and places can be asynchronous as shown in the example. In tabletop rearrangements, some objects cannot directly move to the goal positions. For instance, in this example, objects 1 and 2 are blocking each other's goal positions. In this case, we need to temporarily store one of the objects at a buffer position. A previous work solved this problem with a lazy buffer allocation framework. In the first step, the algorithm decides which object to move to the buffers and the time span for the temporary stay. In the second step, the algorithm allocates free space for the buffers. In the dual arms setting, we face additional challenges. Besides individual picks and places, we need to coordinate handoffs and situations where one arm can clear out obstacles for the other arm. Also, when traveling cost is considered, robot motions may be asynchronous, which increases the complexity of the planning problem. In our paper, we extend the lazy buffer allocation framework into the dual arm setting. In task planning, we treat the rearrangement problem as a path-finding problem in the arrangement space. The optimal solution can be found with A-star heuristic search. For each state, robot arms can execute individual pick and places, a handoff, or a clear and place, where a robot arm clears out an obstacle for the other arm. The buffer allocation step is the same as the single arm scenario. For FC mixspan where robot picks and places asynchronously, we propose a heuristic search algorithm in an interval state space. The detail of the method is shown in our extended version of the paper on arXiv. In experiments, we move objects from randomly sampled start arrangements to an organized goal arrangement. We first compare the execution time of our heuristic search algorithms in both mixspans. The result suggests that considering asynchronous motions is able to slightly reduce execution time, but it incurs significantly more computation time. Therefore, MC is more suitable as a proxy for optimizing the planning process in this problem. Here we show a comparison between our methods and two baseline planners. Single MCHS split applies our algorithm to a single arm setting and then evenly distributes tasks to two arms without considering efficient robot coordination. The greedy algorithm picks and places nearby objects without a long-term plan. We compare them under different density levels D. We note that single MCHS split already performs quite well in a dense environment. The execution time gap comes from coordination failures. For example, an arm idles for a few action steps, waiting for a handoff or object clearance. Comparing with the greedy methods, our method saves more execution time as the density level increases. We also evaluate the performance of our algorithms as the overlap ratio varies. When the overlap ratio is high, less handoffs are needed, but the robot arms spend more time on yielding to each other in the shared workspace. When the overlap ratio is low, there are less path conflicts to resolve in the workspace, but more objects need to hand off to the goal positions. Due to the two factors, the execution time shows a shallow U-shape as the overlap ratio increases. To conclude, in this paper, we apply a delayed verification method into a dual-arm rearrangement scenario. For task scheduling, we propose a heuristic search procedural coordinating handoffs and individual pick and places. Finally, extensive experiments are conducted in Pybolid simulator on workspaces with different overlap ratio rho. Experiments not only demonstrate the effectiveness of our methods, but also provide insights for dual-arm manipulation system design. Thank you for watching.